How do I do this? This is where we left off on Thursday last. How do I divide polynomials? This is the whole reason that we learn long division in the first place. Because there isn't a more effective or efficient algorithm for doing polynomial division at all. So, anybody remember long division?
Did you first start by multiplying the whole thing by 2x? Or the x squared plus x plus 3 and then see what's left over?
I think about the x squared and the 2x plus 3, and the difference is a 2 and an x. So I say, all right, if I divide this part by this part, I should have a 2x. Multiply that through. And then subtract. Those are gone. I get a 3x squared, a minus a 6x, and a 1. And I can repeat the process with these two. The 3 times the x squared to give me the 3x squared, carry the rest of the multiplication through. And subtract. Now in this case, I have a remainder. It didn't divide evenly. And that tells me that x squared plus x plus 3 is not a factor of 2x cubed plus 5x squared plus 1. Just like regular division. I get a quotient and a remainder. There are shortcuts. You can look at synthetic division. You can look at synthetic division only works when your divisor, the thing you are dividing by, is a linear factor. There are other arrangements for divisions, other arrays to write it out, but this base algorithm is inherent in all of those. So what happens if I change fields? I did this over R. R is field. Well, what if I choose a different field? Let's do the same problem. But we'll do it in Z7. What changes? Well, as a matter of fact, a lot of things changes in the middle as well. I've got to do all of my coefficient work in Z7. But that also means that I have to remember what happens when I don't have the right divisor. So I'm subtracting here. I'm okay canceling those. I'm okay with 3x squared, but what happens here? Yes, it should. Thank you. What happens there, though? Aha. Minus 6, I roll it back around to be in Z7. That's plus 1. Okay. I bring this down. Repeat the process. What number goes here? Because I'm working in Z7, I get a 9. There is no 9, it's a 2. I subtract. What happens? I'm going to say sentences that sound stupid. 1 minus 3 is 5. 1x minus 3x is 5x because I'm in Z7. 1 minus 2 is 6. There is no negative 1. Everything else is done the same. My calculations change to work in Z7. I have the same quotient. I have a different remainder at different coefficients floating around in the middle. Try this one. Again, in Z7. Now here's something strange. I know I wrote x minus 2. I could just as easily have written x plus 5. Why would I choose to write x minus 2 as opposed to x plus 5? Yeah.
Does the sign being negative make a difference in our outcome?
Only in the very slightest of fashions. They'd be congruent all the way around, but I have the choice of multiplying by 5, multiplying by 2. The smaller numbers are going to be easier, aren't they? So I could literally pick whichever version I like. Which means up here, I could easily have written minus 2x minus 5. That would still make sense in that universe. By default, coefficients should be positive. But there's no requirement. I'm writing x minus 2 for a reason I will get to in a bit. In Z7.
that be 5x?
Yes, thank you.
Yes.
Careful. That's a negative 10. Negative 10 is positive 4. Think about it. Because negative 10, I got to add 2 multiples of 7, right? Got to get to 14. Oh, that's going to give me a plus 4. Subtract that. All right, wait a minute. 1 minus 4. This is going to be the silliest sentence you've said today. 1 minus 4 is 4. I'm in Z7. 1 minus 4 is negative 3. Negative 3 is the same as positive 4. Okay, but minus 8.
Oh, so it's gonna end up being 0. I'm talking about the major. So 7.
Going to be 6. Negative 8 becomes negative 1 because as soon as I add another 7, it's positive 6, which means it's divided evenly.
I did minus 5x minus 3, and then that ended up getting 4 because when you do the signs.
So here
Right
you
there,
wrote 5x squared.
minus 3x.
Okay, and then we subtract that, right?
Yep.
Which is still going to give me a 4x.
Yes.
Yeah, that works.
Yeah.
Again, I'm trying to think in Z7 where the only numbers that exist are positive, which really makes me more pissed off about that plus 2 on the outside, minus 2 on the outside. But you can do either one. The whole point is to remember the moduli. I have to do everything mod the appropriate base in this case. 7. Wait a minute. This divided evenly. I factored my polynomial. And now I see the reason I want to do minus instead of plus. I certainly could do x plus 5. Right? That's still the same. Yes, Noah?
For whenever we write this, do we have to put in the end in Z7?
Yeah, I got to know what field I'm in. Yeah. Otherwise, I am doing all of this in R by default or by Z by default. I really want to know what field we're working in. I could continue to factor. Remember, in a field, factoring works because almost more than just the distributive rule, because the distributive rule is true in every ring. What's special about a field? And technically, Z7X, Z7 is a field, but Z7X is an interval domain.
But by definition, computed? Is that why?
No, because that's just commutative
Oh,
rings.
sure.
I need to go further.
Because of things in it.
And that means there are no zero divisors. So factoring works. Which means I can take this a step further. Because I know how to factor a quadratic. I've been doing that for a very long time. But having gotten from here to here, What does this factored version tell me? What information do I glean from the factored version? Oh, come on, people. This is a regular algebra question, not an abstract algebra question. Why do you factor? To find the roots. And that was equivalent to finding the homomorphisms, phi A, that these polynomials would be in the kernel of. Okay, wait a minute. I've collected the idea that connected, the idea that roots and homomorphisms go together. Factoring now goes with that. So I can write up the exact same result we had in Algebra 1, the factor theorem. So the reason I wrote x minus 2 as opposed to x plus 5 is because x minus a is the piece that shows me the factor. That means that a itself is a root. Well, a being -5, -5 in Z2 is the same as +2. So by writing them all as subtraction, I could write another version of this factored polynomial as x minus 2, x minus 3, x minus 6. Just look at one number for me. In the original polynomial all the way up here on the left, what's the constant term? Does it make sense to have 4, 5, and 1 over here? Seems pretty damn weird, doesn't it, right? 4 times 5 times 1 is 20. In Z7, that's 6. On the other hand, 2 times 3 times 6 is 36. But it would be negative, wouldn't it? Negative 36 in Z7.
Go down to 42, so you have remainder 6.
6. Does it work the same both ways? Absolutely. But having it write x minus a allows me to use the factor theorem. I know exactly what the roots are by finding the factors that divide in evenly and pulling them out. But that means within a field, I can, as you saw me do here, find a root, divide it out, have a smaller degree polynomial. Find a root, divide it out, have a smaller degree polynomial. So I went from 3 to 1 and 2 to 1 and 1 and 1, reducing the highest degree in my system, recursively, inductively. Which leads me to one of the biggest results in all of algebra. Something you've been using for probably 7 or 8 years by now in your mathematical career. As a matter of fact, we did this in Calc. We did this in Calc 2 and 3, all finding all those critical points, right? You take a polynomial, you set it to 0. How many places do you have to look for? Whatever the power is. We knew this rule. We didn't know why it worked. Well, now I know why it works. All I do is I do an inductive argument using the factor theorem. Questions? The question that is before us, that is a much larger part of this course, is can I guarantee that I can find the right field where I will always have exactly n solutions? Can you guarantee some field where I can completely factor, as we did up here, and get all the roots to that polynomial? Does it always work? I guarantee you the answer to that is no, because you've done it already. I'm going to give you a field, and I want you to come up with a polynomial that has no roots in that field. Polynomials whose coefficients are rational numbers. Can you find me a polynomial whose coefficients are all rational numbers, whose roots aren't? Huge hints. You did this in discrete. We talked about it on Thursday. I didn't use these terms back in discrete.
I feel like any polynomial that results in like you having to use a quadratic formula and making a square root.
So give me a really easy one. Ready? And technically, I really don't even have to use the quadratic formula on this one, Reese. Right?
No.
The roots of that are plus or minus the square root of 2. And we've already proved that's not a rational number. On the other hand, I can think of those coefficients not just as rational numbers, I can think of them as real numbers. And in the real numbers, the square root of 2 is part of the field, isn't it? Okay, wait a second. So if I'm in the field Q, every non-zero element's a unit, this polynomial can't be factored. But if I change fields, it can be factored. A number that has no factors is called prime. A polynomial that can't be factored is called irreducible. And I think of irreducible, I can't reduce the power as I factor. Linear factors are irreducible. Because there's no way to make the power any smaller than 1 by factor. But anything that can be factored is therefore reducible. You got to find the factors. All right, wait a second. Is this irreducible or not? How do you know?
We could toss it into the quadratic formula, and it would give us an answer. I guess we don't know that it would give us an answer in Z5.
As a matter of fact, if I do this using the quadratic formula, I get complex numbers as roots. Because that's x squared plus 2x plus 1 plus another 1, right? So that's x squared plus 1 x plus 1 quantity squared plus 1. The roots are complex. I'm in trouble now, man. But you already did this in the homework I gave back. To find out if something's reducible, by the factor theorem, you need to find out if it's got a root. If this number is a 0, if and only if this is a factor. If this has factors, it's got to have roots. We're in Z5. Only 5 numbers to check. So start checking. What happens when you put in 0? That's not a root. What happens when you put in 1? I get 5, which is 0. Aha, I have a root. Now here's where you have a choice. You could use x minus 1. You could also use x plus 4, because we're in Z5. So I know right now that I'll get a factor of x minus 1. I don't know what the other stuff is, but what do I know about the highest power in the other stuff? Say again?
I said the highest power is to the second.
That's over here. What do I know about the highest power over here? Which means there'll be another linear factor, which means there should be another root. If I plug in 2 squared is 4, plus another 4, plus 2 is 10, which is 0. It's reducible. I reduced it. This idea really only works if the order of the field is fairly small. If I was trying to do this in Z37, I'd be here for a week. I don't want to think about it. However, it's worse than that. Even this process doesn't always work. The factor theorem says that I have a reducible polynomial when I have a root. If I have a root, then I know a factor. Yes? A is a root, then x minus a is a factor. But let's consider in R of x, the real numbers, x to the 4th plus 5x squared plus 4. Can you factor that? I don't want to try plugging in because there are infinitely many things I could plug in and that would just suck. So let's go back to using regular, ordinary algebra techniques, no funny tricks, no nothing weird. Can you factor that?
Would it be x squared plus 4, x squared plus 1?
Aha. So that's reducible. Yet, it doesn't have any roots in R. So it turns out I end up with a very restricted result. If I have a polynomial of degree 2 or 3, then it's reducible in fx. We're going to say reducible over f. Reducible over the field f, if and only if it has a 0. And this is my counterexample as to why you can't do this for all degrees. It only works for cubics and quadratics. As soon as I get to degree 4, it's possible to reduce without having any roots. Here's the problem. The quadratic formula is roughly 3,500 to 4,000 years old. It was known in Babylon and Egypt. We have evidence of it being written up. The ability to solve quadratic equations was written up using completing the square in Babylonian mathematics tablets that are about 4,000 years old. The cubic equations were not examined in detail till the mid-1500s. I got 3,000 years where nobody did anything with this crap? Yes. Because in and of itself, solving those equations was not done algebraically until the development of algebra, which is the 1400s and 1500s. Crap. Well, the Western analysis of algebra happens around then. The Eastern analysis of algebra happens in about 1200 or 1400, and it slowly makes its way westward. So we're behind the times here, people. But between 1500 and 1700, we get a degree 3 formula, we get a degree 4 formula. People are like, as long as I can reduce things down, this is going to work. And then all of a sudden, this result comes into play. A lot of people go, well, now I have a problem, because even in my favorite set of numbers, the real numbers, I can give you a reducible polynomial that doesn't have any roots. Fine. Figure somewhere around this. So, in an effort to try and understand what was going on here, most people started working with the rational numbers. And in order to work with the rational numbers, it turns out behavior in the integers is actually really important. So when working over Q, working with polynomials in QX, turns out that your integer roots actually matter more. Now here's an interesting note. The integers are not a field. The integers are an integral domain. And the polynomials with integer coefficients, Zx, is also an integral domain. So I'm actually working not in a field at this point in time. but we wanted to look at rational numbers. So let's think about factoring, even though we only have integer coefficients, let's think about factoring over the rationals. It turns out f of x factors in two polynomials of degree in Qx if and only if f of x factors into two polynomials of lower degree and it's the same lower degrees over the integers. If you want to know whether or not you can factor rational numbers, you only have to try and factor in the integers. As long as your coefficients were integers to begin with. All right, wait a minute. Why does that work? It works because of an idea that I skipped over in this semester on purpose. The integers are an integral domain. They're not a field. I want to build a field, and that field should contain the integers. Now, the method for doing this, I believe it's in chapter 22 in our textbook. I skipped it on purpose. It is literally an entire lecture where I do nothing but prove it is possible to build a field out of an integral domain. I think you would barf on me after 75 minutes to do one proof. So I didn't do it. But it turns out that the field we make out of the integers is the rational numbers. That's the way we build the rational numbers. They are the smallest possible field you can get using integers as your starting point. They, in a fashion, complete the field that we want to have the integers inside. I didn't bother to build it. For the purposes of this class, it's kind of useless until I hit this result. And realize that the reason this works is because the integers help me build the rational numbers. But what this means is I never have to worry about trying to factor integer coefficient polynomials outside of integers. If it doesn't factor in the integers, it doesn't factor in rationals, which guarantees me irrational roots. I just found a way to prove that the square root of 2 is irrational by looking at the polynomial x squared minus 2, whose coefficients are integers, and then showing you don't have any roots in the integers, you don't have any factors in the integers, so you don't have any factors in the rationals. Why do I know it has no roots in Z? This is an algebra answer, not an algebra answer. So why do I know that there are no roots in Z?
Because if you solve for x, you get an irrational number.
I don't know what irrational means yet. I just want to show there are no integer values that work, right? Once I get beyond 2 or negative 2, my answers are big, they're positive, right? And negative 1, 0, and 1, when I plug in, give me negative answers. In order to go from negative to positive, you have to go through. I have to go through 0. And I skipped it. I went from negative to positive without ever hitting 0, there are no roots. And if it has no roots in Q, then those numbers must not be elements of Q. Congratulations, you found a new proof that the square root of 2 is irrational. Well, you found a new to us proof. It gets even better. Remember, I asked you to look at the last term in our cubic equation, ended with a 6, right? And I looked at the roots. Turns out, if I have a polynomial whose leading coefficient is 1, and it's got integer coefficients. And A0 is not 0. Because if A0 was 0, I'd be able to factor out an x. Let's suppose I don't know anything about this polynomial p, except it's got integer coefficients, the last number is not 0, and we have some root that is rational. Then p of x also has a root that is an integer. In other words, if you have a rational root, you must have an integer root. But wait, there's more. And that integer root divides your last number. Why did I say it was nicer to write it as 2, 3, and 6? Because 2 divides 6, 3 divides 6, and 6 divides 6. Didn't pull them out of my ass for no reason. Wait a minute. X squared minus 2 is a polynomial that meets this criteria, doesn't it? Its leading coefficient is a 1, and it ends with a non-zero number. There are no integers that divide the last number that are roots. What divides 2?
2 and 1.
And -2 and -1. And if I try all 4 of those, none of them are roots. There are no roots that divide the last number, therefore there can be no roots in Q. I just did the contrapositive. whatever the roots are to that polynomial, they must be irrational. The goal of algebra is to solve equations, to find roots, to factor things. So, let's give it a whirl. Problem number one. This may or may not be reducible the easy way. But let's make use of the theorem we just proved. Because the leading coefficient of this polynomial is 1, it ends in a non-zero term. If it has a rational root, then it must have an integer root. If it has any rational root, it must have an integer root. That's what our theorem says. And that integer root must divide the last number. What are the things that divide 1? So plug in 1, plug in -1, tell me what you get. So what does that mean? And if there's no integer roots,
There can't be any rational roots.
there are no rational roots, which means no linear factor. X minus a divides this. The form x minus a, where a is any rational number, can't divide into this, which means this is not reducible into a power 1 and power 3 over q. Over. Remember, our theorem said it factors into two polynomials of lower degree in the rationals if and only if it factors into two of the same lower degrees in the integers. I can't factor it in the integers, therefore I can't factor it in the rationals to 1 or 3. But this is a degree 4. I might be able to factor it in something else, which would be a pair of quadratics, right? Like we did with the x to the 4th earlier. So there's another option here. what if f of x can be reduced to p of x, q of x, with degree p equals 2, and so is degree q. Well, here's the fun part. What was the leading coefficient of our function in this problem? The leading coefficient. Number at the very front is 1. X to the 4th, right? Which means then this would have to factor into 2 quadratics, and they would both have to start x squared. Because remember, we're factoring over the integers to start with. Well, if that's the case, then there'll be some ax and b here, and some cx and d here. I need you to do me a favor. I need you to multiply this out and gather all your like terms. The only way to get a cubic term is to multiply the x term from one parentheses with the x squared from the other. So I'll get an ax cubed from the first set of parentheses, and I'll get a cx cubed from the second set of parentheses. A plus c, x cubed. The only way to get an x squared is to either multiply the constant term by the x squared term, or the x term by the x term. Bx squared, dx squared, or ac x squared. The only way to get an x is to multiply the x by a constant, ad or bc. The only way to get a constant is to multiply the constants. Right? Let's equate some terms. Here, bd must be equal to 1. I'm in the integers. That means either they both equal 1, or they both equal -1. Because that's the only way to get two things to multiply together to give me 1. In either case, they're equal. So let's go to the linear term. AD plus BC has to be equal to 8. Yes? But B and D are the same. So that means that AB plus BC equals 8. And that means that B times A plus C equals 8. And now my brain goes, wait a minute, I have a problem with that. Why do I have a problem with that? A plus C comes from the cubic term. There's no cubic term on the left. Because we're in the integers are an integral domain, no zero divisors. I know that B is not 0. I know that the product of B and something is not 0. Therefore, the something can't be 0. Oh, shit. No such factorization exists. That means my function is irreducible over the rational numbers. The only roots that that polynomial has, all 4 of them, are irrational numbers. Factoring is hard. So maybe we'd be better off trying to figure out what things are not factorable. That's what we just did here. We figured out, hey, this polynomial f of x that I just wrote down, it's a prime. Well, it's irreducible in the rational field. Sorry, yes, the rational field. But I was working in other fields. I like working in the rational numbers. And along came a guy by the name of Eisenstein. The Eisenstein criterion says, let P be a prime. And pick some polynomial whose coefficients are all integers. If a n is not congruent to 0 mod p, but all the rest are congruent to 0 mod p, and the very last one, a0, has to be 0 mod p, but it has to be not 0 mod p squared. I don't know how the hell he came up with this. He said, if those 3 things are true, then f of x is irreducible over the rationals. There are no rational roots if the Eisenstein criteria is true. So let me go back and look at that particular polynomial we were just looking at. Pick a prime number. Was wrong. I made a copy error. Stop. 1 less than or equal to I less than. So A0 does not have to be congruent to zero. One exception. All the ones between the first and last need to be congruent to 0. Pick a prime number. I'll make it easy. Let's use 2. P equals 2. A4 is 1. That's definitely not congruent to 0 mod 2. A3 is 0. That's congruent to 0. A2 is negative 2. That's congruent to 0. A1 is 8. That's congruent to 0, all mod 2. And A0 is 1, which is definitely not congruent to 0, but not mod 2. We're looking mod 4. Here's yet another way to show that this polynomial has no rational roots at all. You cannot factor this with fractions in the factors. Period. Whether you try and factor into linear terms or quadratic terms, you got to have irrational numbers in there. Try this one. Does this have a rational root? Now, I remember back in my algebra class, all those many years ago, a result called the rational root theorem. And the rational root theorem allowed me to start looking at possible rational roots by taking things that divided the last number and things that divided the first number and making a whole bunch of fractions and testing them all. But in that case, what are the factors of 12?
1, 2, 3, 4, 6.
And 12. And the factors of 25 are 1, 5, and 25. So I would be making 6 times 3, 18, 36 different fractions to try out, because the positives or the negatives. I think I'd rather hit myself in the head with a steel bottle. I don't want to do this. Pick a prime number that divides not the first one, not the last one, but the ones in the middle. Nice and easy, right? Pick 3. Let's see if we pass the Eisenstein criteria.
Boom, 3 divided 12.
Ah, but the last number,
Oh, last number squared.
I look at p squared. Ah, whew, I got away with it. Because 25 is congruent to 1 mod 3. A4 is 9, that's congruent to 0. A3 is 0, that's congruent to 0. A2 is negative 3, that's congruent to 0. A1 is 0, that's congruent to 0, all mod 3. And negative 12 is congruent, not congruent to 0, mod 9. Because I'm working in p squared there. So this polynomial is irreducible. No roots in Q. Now, I must tell you, if I know there's a rational root or an integer root, finding it is probably best done with the rational root theorem. But rather than just blindly start testing 36 different roots, I can say, no, I don't have to test any of them. None of them are going to work. The best part. Factorizations of polynomials are unique in a field, up to congruence within that field. If it's irreducible, then we're stuck. But if it's reducible, then we can factor it into a product of irreducibles. Oh, every non-constant polynomial in fx. So once you know you can factor, either your polynomial can't be factored at all, it's irreducible, that's one irreducible polynomial. Or it can be written in a reduced form, and then that's unique up to order or multiplication by units. If you put a 1/2 here and a 2 there, that's the same polynomial, right? So if I include units differently in different places, it doesn't make a difference. So, knowing that I have a polynomial that is irreducible in a given field, can I find another field where it is reducible? Can I make my fields bigger? We'll talk about that after the break. That's all. Have a wonderful week. I will see you all a week from today.
Was that section 27 and 28?
We finished 27 at the end of last time. We just finished 28 this time.
Enjoy your Thanksgiving.
Thank you.